Okay, today we discuss the first law of thermodynamics, which expresses the conservation of energy. And the first law, written mathematically here, says that we can change the energy of a system if we have a heat flowing into the system or coming out of the system, if we exert a mechanical work to the system. And these first two terms for an open and reversible system, I can write them as the first one, the heat exchange is TdS, the work exchange is PdV, and there is also another term here in my equation, is mu times dN. Mu is the chemical potential, dN expresses the change in the number of particles. So the system is open, so it can exchange particle with the external reservoir. All right. The next step is to write then the energy of a system as a function of state variables. Now, S, V, and N. S is the entropy, I forgot to say. V is the volume, and N the number of particles. So I write the energy now of the system as a function of S, V, and N. And if I do so, I can just use basic mathematics. E, the energy, is a function of three variables, so a variation of the energy is given by partial derivatives of the energy with respect of these three variables, dE ds, derivative at constant volume and constant number of particles, times ds, dE dV times dV, dE dN times dN. But if I have now this relation, I can identify now what is the temperature, the pressure, and the chemical potential, because I can equate the first equation and the second equation for dE. So connecting now the two equations, I find that the temperature is given by the derivative of the energy with respect to the entropy at constant volume, at constant number of particles, and so on. The pressure is minus dE dV, again at constant S and constant N, and chemical potential is the dE over dN at constant entropy and constant volume. Okay, so this is the first set of thermodynamic relations. The first one we are going to use, the one for the temperature. The other two are not very practical, so why they are not so practical is it's difficult to think of a system where I have entropy as a control variable, right? Because normally, how can I think of making an experiment, right? You can control the volume of a system, you can control the number of particles in the system, but you know, how do you control the entropy? How can you change the entropy of a system? It's not very clear. So this three variable, the entropy, it's a bit problematic as a control parameter. So that's why we do the next step and we do a transformation now. So the transformation is the following. Let's rewrite the heat as a slightly different differential. So it's the differential of Ts minus S dt. It's a very simple mathematical identity. And now I bring the Ts in the differential to the left side of my equation, and I get a derivative, a differential of now a new function, which I call the free energy, Helmholtz free energy. E minus Ts is my Helmholtz free energy, and now it will be expressed as a variation minus S dt minus PdV plus mu dN. Okay, so this is a mathematical transformation. We have introduced a new thermodynamic quantity, the Helmholtz free energy, which normally is indicated by F. And now the control variables are the temperature, the volume, and the number of particles. See, we haven't modified the terms P dV and mu dN, but we have changed the term which originally was written as TdS in minus S dt. Good. So now we have this new variable F, which is E minus Ts, okay, and our Helmholtz free energy. I do the same trick as I did before, when I differentiate this Helmholtz free energy, now the control parameters, the controlled variables are T, V, and N. So it's easy to see with the same trick that the F dt at constant V at constant N is minus S, minus the entropy. And so on, the pressure is minus dF dV, and the chemical potential is dF dN. So I'm just playing with the same first law of thermodynamics, but using now different variables with respect of, so I got rid of the S, of the entropy, and I use now instead the temperature. Yeah, so we can repeat the same trick. Now we have seen number one, it was our original formulation where as control variable we use entropy, volume, and number of particles. We move to 2, we define the Helmholtz free energy, which is a function of V, N, and T. So I made this change from S variable, S entropy, to the variable T. If we do a transformation now, number 3, and we change exactly in a similar way, but now the term with the work. So we don't like to have V as a controlled variable, but we would like to have the pressure as a controlled variable. And I suppose that we experimentally don't keep volume constant, but we work in pressure, for instance, atmospheric pressure. Then we introduce, it's a natural, introducing a new variable, which is the enthalpy H, which is E plus PV. And now this, the state variable of the system is that instead of the 1 where we have S, V, and N, now we have P, S, and N, right? We change the V dependence into a pressure dependence. And we can make the final step, the number 4, which is 2 times the transformation 2 and 3 combined together, and that will give us a new thermodynamic variable, which is G, which is defined as E plus PV minus TS. The way we work, it's exactly the same as before, right? This is not the only possibilities, this 1, 2, 3, and 4. We could have done something also with the chemical potential and change the N and mu, and we will have other combination of variables. But normally we will work with these 4 different transformations, and particularly with the number 2 in statistical mechanics. Okay, so we have seen these 4 different thermodynamic quantities: the energy, second, the Helmholtz free energy, the enthalpy, and the Gibbs free energies. Okay, and when we worked the first law of thermodynamics in the first set of variables, the E, the energy, so we derived the equation 1 over the temperature is the derivative of the entropy with respect of the energy, constant volume, constant number of particles. From the second set of variables, so when we have use the Helmholtz free energy, we derive that the pressure is minus the derivative of the Helmholtz free energy, dF over dV, at constant number of particles and constant temperature. But now you can continue, right? You can use the first law of thermodynamics, and for instance, an exercise is what is the derivative of the enthalpy H over P? P in the set was one of the control variable. You know, when we use enthalpy, we think of P, S, and N as control variable. So the question is, for instance, for us is solve this quantity and find it out. So this is a small exercise that you should be able to do. Now, another concept that I would like to recapitulate now is that the difference that you have seen in thermodynamics between extensive and intensive variables. So what is the difference between these two? So imagine that you have a system, a homogeneous system like a gas or a liquid, a thermodynamic system, and we divide it into 2 parts. Okay. Now let's divide it into 2 parts. Like imagine that there is a gas in a container. Let's divide it into 2. Okay, so the extensive variables are those that are also filling this division. They become twice as small, right? So if the total energy of the gas is E and I divide it into 2 and I consider only half of it, then the energy would be E divided by 2. The number of particles, if the system is homogeneous, would be N divided by 2. The volume will be V divided by 2. The entropy will also decrease, right? So these are extensive variables. When I divide my system in 2 or in some parts, these extensive variables will become small, will be divided by the number of parts that I'm dividing the system to. But there are other variables that are intensive. They will not feel that we are dividing the system. For instance, if we have a gas and we consider half of it, okay, we consider half of it and we're measuring the temperature in this half. The temperature is the same as in the other half, right? So the temperature is an intensive variable. Also, the pressure will be the same, and the chemical potential will be the same. So we have these two different type of variables, right? And now if we go back to the set 1, the example 1, so you see we write the energy as a function of S, V, and N. So what is peculiar of this is that all these variables are extensive, right? Whereas you see when we go to the Helmholtz free energy, the F, now we have changed the S, the entropy. We made a change of, with the change that I explained, is S is replaced by a T. So we are exchanging one extensive variable into an intensive one. So, but it's a very peculiar property of the first relation, where E, when we write the energy as a function of S, V, and N, all these quantities are extensive. Okay, so we have seen that the energy, so the first relation contained energy, entropy, volume, and number of particles. They are all extensive. So what does it mean? How can we see this extensivity mathematically? So let's consider alpha as a real positive number. Okay, extensivity mathematically means that if I have this function, and if I multiply all the variables this number alpha, then the result must be equal to alpha times the E, right? Because I'm, so when I multiply by alpha, so for instance, if alpha is a factor of 2, I'm considering a system that has twice as much as entropy, twice as much as volume, twice as much as number of particles. So this extensivity must give me that I get twice as much as the energy of the original system. Okay, so this is the relation. Okay, this alpha is a generic number, a real number, positive. Okay, so multiplying by alpha, meaning that I'm scaling the system. I'm making twice as big. Alpha is equal to 2 or 1/2. So I divide it in 1/2, so alpha is 1/2. Okay, now let's do a little simple mathematical step. Let's apply the differentiate. Take the total derivative with respect of this parameter alpha in the first and in this equation, right? So then if you differentiate with respect of alpha, this function E is a function of S, alpha V, and alpha N. So we have to differentiate. This alpha is in all these three variables, so we have to differentiate dE with respect to ds, and then we have to differentiate alpha S with respect of alpha, right? But this will give simply S. So we have a first term, ds, which multiplies by S, then the second term, dE dV times V, and dE dN times N. And the derivative with respect of alpha of the term on the right-hand side, which is just alpha times E, is just E, right? So I'm differentiating alpha, and that it's 1. Okay, good. Now we are done, because if we use the thermodynamic relations that we derived at the beginning of this lecture, dE ds is just the temperature, dE dV is minus the pressure, and dE dN, okay, is the chemical potential. So very generically, we have derived what is called the Euler relation. This Euler relation tells me that T times S minus P times V plus mu times N is the energy of the system. Okay, this is very, very general. So not deriving it for one specific system, for a gas, for an ideal gas, for a liquid, for any thermodynamic system, this holds true, this Euler relation. And now if we manipulate it a little bit and we bring the TdS to the right-hand side and also TS and PV to the right-hand side, we keep mu times N is equal to E plus PV minus Tn. But this is what we define as the Gibbs free energy. Okay, so this Euler relation tells me that this Gibbs free energy is also equal as the chemical potential times the number of particles. This Euler relation can be seen also like that the Gibbs free energy is the chemical potential times the number of particles, or that the chemical potential is the Gibbs free energy of the system divided by the number of particles. Okay, so we can conclude this first part of recapitulation of thermodynamics by considering phase equilibrium. So we are asking ourselves, what does it mean that when can two phases be in equilibrium? And now I made this drawing on top of the blackboard. We have the phase 1 on the left side of a container and the phase 2 on the right side of the container. For instance, phase 1 could be ice and phase 2 could be water. So sometimes during the year, for instance, we see that ice and water can be simultaneously found, right, when it's winter, and we know that in that case the temperature is around 0 degree, because that's the only possibility is at around that temperature that these two phases coexist. If the temperature is too high or too low, that you only find ice. If it's too low, if it's too high, you only find water, and so on, okay, in your system. So the setup is the following. Let's consider a system which is isolated from the external world, so there is a thick wall in the system, and let's consider situations where there is a phase 1 and a phase 2, so there are two phases in the system, so the system is not homogeneous, and as in the case we discussed so far, but it's made by two parts. One is ice and one is water, and this thin line is an interface between the two. Okay. And now let's consider, instead of what we did before we wrote the energy as a function of controlling parameters, the entropy, number of particles, and volume. Okay, now we reverse this relation and we consider a relation which is giving the entropy as a function of the energy, number of particles, or volume. We assume that this inversion can always be made. Okay, and now it's better to consider this S as a function of E, N, and V. So what is E? Is the energy of the system. But now the system has two parts. The system has an energy E1 as an energy E2. So the phase 1 has an energy E1, the phase 2 has an energy E2. This generally E1 and E2 will be different, right? The volume of the phase 1 will be different than the volume of the phase 2, and so on. The number of particles in the phase 1 and 1 will be different than the number of particles on the phase 2. So instead of having just E, N, and V, we have E1, V1, N1, E2, V2, and N2. Okay? So our total entropy will be the sum of these two entropies, right? So to be thermodynamically correct, one should also include the fact that there is an interface, but this interface is very thin, okay? And if our system is very large, we can neglect this interfacial contribution, but which is important in other situations, okay? So the total entropy is the sum of the two entropies. And S1 and S2 are different functions, right? Because one, for instance, can describe a gas and the other a liquid. One describes, in this case, example, ice and water. One describes a solid and the other one describes a liquid. Okay, so S1, S2, we have to imagine they are different functions, right? Okay, but what is now what we are asking? We are asking that our system is in equilibrium, right? So that the phase 1 and the phase 2, they are there, they coexist, and they have reached a situation of equilibrium. We can imagine that we have an isolated system. We prepare the system, suppose that there is only water, but then the temperature is such that, after some time the ice forms, okay, and if we let the system relax for sufficiently long time, the system will reach an equilibrium situation where there is ice and water, okay, it's in equilibrium. So the entropy will have reached a maximum, right? The entropy always, if entropy would not be maximum, right, the system will change again and reach a maximum. So the equilibrium condition is that the entropy is a maximum. So if I take any variation of the entropy around that point where I am in equilibrium, I will get 0 because this is a condition for a maximum. A maximum is an extreme point. So what can the system do, right? The system is isolated, so the number of molecule of water in our system, so H2O, the number of molecule will stay the same. There is no communication with the external world, but so the n, total n, will be fixed, right? Because there is no exchange. Total n is fixed, but n1 and n2 can change, right? Suppose that we start from an initial situation where we have only water, but then it's slowly crystallizing and making ice crystals in our system. So the total n will be only, n2 will be equal to n, or initially, but then after some times n2 becomes smaller and some molecules will go into the ice phase, so the n1 will take a value which is non-zero. Okay, so we are in this situation. But now let's suppose that we are in equilibrium. So once this equilibrium has taken place, right, we must have the variation of S with respect of this. All the parameters must be equal to 0 because S has to be maximum, the entropy. Okay, so the last line of our in the blackboard expresses this mathematical condition of equilibrium. So variation of S. So what is the variation of S? I can vary S by varying all the variables, E1, V1, N1, E2, V2, N2. And so the line is just all this partial derivative. So I write ds1 dE1, the first derivative, times dE1, the differential, so on and so on. Okay, so I didn't write that this derivative has to be understood as, for instance, ds1 dE1, a constant V1 and constant N1, and so on and so on. Okay, right. Okay, so we are at the last line of the blackboard, and now this last line continue, like follow the arrow up to the right part of the right top of the blackboard. So we have to realize that when we make this variation, E1 and E2, right, the two energies, they are not, I cannot vary E1 and E2 arbitrarily. My system is isolated, right? So the total E, or the total number of particles, or the total volume, they are constant, right? So this variation must be such that E1 and E2, they vary, but if E1 becomes a bit bigger, E2 must become a bit smaller, right, to keep the energy constant, total energy constant. So in fact, because the energy is constant, it means that dE1 plus dE2 must be equal to 0, right? Okay. So, and if you use this condition, you see that the terms on ds1 dE1 must be equal to the term ds2 or dE2, because this property of ds equal to 0, right, is a global property. It varies for any arbitrary transformation. So I can set dVs and all the dVs and dN equal to 0 and making only a variation on energy. And I still have to have this condition. So finally what we find that ds1 d1, so this derivative of the entropy of the phase 1 with respect of the energy of the phase 1 must be equal to the derivative of the entropy of phase 2 with respect of E2. But if we think back, what is this? This is exactly what we are saying, and this is concluding that the temperature T1 it must be equal to T2 because the S over TE is 1 over the temperature. Okay, so that's the condition. So we find that this derivatives is giving connecting this and keeping constant the total energy. There must be a the two temperature. The temperature of the phase 1 must be equal to the temperature of the phase 2. Okay, so now we are at the end. So what we find by this, if the energy is constant, the volume, total volume is constant, and the number of particles is constant, we find that necessarily the temperature T1 must be equal to the temperature T2. The pressure also, P1, must be equal to the pressure of P2, and the chemical potential must be equal. So the result is that two phases coexist if they have the same temperature, if they have the same pressure, and if they have the same chemical potential. This equal temperature means that there must be thermal equilibrium that we knew, right? So that's what we said. Two phases they have to have the same temperature. They have also to have the same pressure, right? Because otherwise, they are not in equilibrium. And if the pressure are different, there is no mechanical equilibrium. There is more force of one phase, the phase 1. It applies a higher force compared with what the phase 2 applies to the phase 1. Okay, so if the pressure are not in equilibrium, the interface between these two phases will start moving, right? And finally, there must be a chemical equilibrium also. The chemical potential of one phase must be equal to the chemical potential of the second phase. So what happens if the temperature are different? Then there is an exchange of energy of one phase and the other phase until the equilibrium is found. If the two pressures are different, there is an exchange of volume between these two phases until the mechanical equilibrium is found. And if the two chemical potentials are different, there is an exchange of number of particles. So particles move from one phase to the other, and they exchange. There is a change variation in N1 and N2 until this situation is found. This is a situation of maximal entropy. Okay, so this is very important because it will come back later in the course. Remember, so two phases are in equilibrium, can coexist only if there is thermal, mechanical, and chemical equilibrium, expressing these three relations.